Now I'm going to talk about example 2 in Lab 2, and for this there's no data set per se. I just want to introduce you to a couple of our functions related to probability density functions. You remember in lecture I was talking about z tables and t tables and saying that while it's good to be able to read these tables, when we have R, we actually do not need to refer to these tables in the books, which often will just give you approximate values because clearly there's only certain cases that are presented in these tables, but that we can use R to get exact p-values or exact z-scores or t-scores as long as we know those functions. So let's focus here first of all. Let's look at the z-table. The way this is set up is that what this table gives you is the area to the right of a certain normal score. If we were thinking about a type 1 error rate of 5%, say, that would imply that we have 2.5% of the area of the curve to the right of this particular value. And if we go down into the table here, 2.5% is right here, and that corresponds to a z-score of 1.96. Now, in RStudio, there is a function called qnorm. And what this function does is that it gives you the z-score that is associated with a certain probability under the curve. Now, the way R does it, though, is that it thinks the area to the curve, area that you're interested in, is to the left of the value rather than the right of the value. So if I were to put in 0.975 and run it, what I get is 1.96, which is exactly what I would expect 1.96 to have 2.5% of the area to the right. R does it with area to the left. So if I have 2.5% to the right, then I have 97.5% to the left. I can override this default in R by using this lower dot tail parameter, and I can turn it off. I can say, I want you to, R would like you to interpret this 97.5% as not being in the lower tail, but being in the upper tail. And if I do that and ask about 2.5% in the upper tail, what you'll see is I get exactly the same z-score. In other words, if I have a z of 1.96, 97.5% of the area is to the left, or 2.5% of the area is to the right. And what I would encourage you to do is go into the z table if you're comfortable with reading off probabilities here, and make sure that you can program R to give you the values that you would expect. In similar case, we have a function for, I guess I should say, you can go the other way around too. qnorm gives you the z-score, but then there's another function, pnorm, which again is with the normal distribution. So these are z-scores we're talking about. But what this is going to do is return to you the p-value, or the area, given a specified z. Now, what I'm going to do is I'm going to copy the z-score that R just said was associated with those probabilities and throw it in there. And what it's telling us is indeed to the left of that z-score is 97.5% of the curve. And just like with qnorm, I can override this. I can do lower tail equals false for the same z-score, and hopefully, and it does, hopefully it's going to tell me that 2.5% lies to the right. So this is very powerful. It's very, very quick, and you can get exact probabilities that you really don't have access to in these limited tables that you may have in your book. Like with the normal distribution, R has probability density functions where you can pull values and also their associated probabilities for t distribution. And the function for that, instead of qnorm, it's qt. So if I say qt with 97.5% to the left, and with t distributions, there's an additional piece of information that you don't need with normal scores, and that is the degrees of freedom. So if I say 10 degrees of freedom, we have, say, 11 measurements in our sample, and I throw this in, what you'll see is we get a higher t-score than we do for a z-score given the same probability. And this is exactly what we would expect and what I talked about a little bit in lecture, that for any given, for example, type 1 error rate, you're always going to end up with a higher t-value than a z-value. And that's the price you're paying for not knowing the true variance of the population. The inverse function of QT is PT. So if I say PT and I grab this t-value and specify the same degrees of freedom, I end up right back where I started, back to 97.5%. If you go to example 2, I'll show you the equivalent functions for chi-squared probability distributions, density functions, and also for F distributions. So there you can always get a probability given an F or chi-squared value, and you can always get the F or chi-squared value given the probability. And so that's just something for you to play around with a little bit and to make sure that they're behaving appropriately. And the reason it takes a little bit of work is because, at least for me, the way it assigns area to the left rather than to the right of the curve is exactly opposite of how I've always used those tables. So you can, you just have to be careful and be aware of that. Also, in the example 2 script, I gave you some code at the bottom that plotted these different density functions. That is not something critical for the course, but I'm going to try to throw at you just different examples of things you can do in R in terms of presenting things graphically. All right, that's it.